Hello, and welcome to 2.3 Applying Newton's Laws of Motion. I think this is a fun lesson because we're not really learning any new concepts, we're just sort of looking at some challenging problems and trying to understand how to approach them. So, we're going to look at two types of problems. One where our objects are in equilibrium, and equilibrium is when an object has no net force. That's when an object is in equilibrium. So this means that the net force is equal to 0. And we can extend that. If the net force is 0, that means that the net force in the x dimension has to be 0. And the net force in the y dimension also has to be 0. That gives us a lot of extra information to solve a problem. So the first two problems we'll look at are objects in equilibrium. This problem says that a sled has a mass of 14 kilograms and is on a hill that is inclined 25 degrees to the horizontal, as shown to the right. The hill is very icy, which means there's basically no friction, and the sled is held at rest by a rope attached to a post. The rope is parallel to the hill as shown. We want to draw a free body diagram. So, free body diagram, I have my box, I have tension acting up the hill like this, and that's acting at this angle of 25 degrees. Okay, and I have gravity acting, of course, straight downwards. Gravity is always straight towards the Earth. And I have a normal force perpendicular to my surface. Normal force. And this was tension over here. Okay, so that's our picture. I can say that the net force is equal to 0 because it says this is tied to a post and it's not going anywhere. Now I've shown sort of the angle for the tension force, but what we can actually do is break up the gravity into a component that's perpendicular to the surface and a component that's parallel to the surface. And you can see that if I do that, then this internal angle is going to be 25 degrees as well. And if you're not clear about that, we can look at that in class to really see where that 25 degrees comes from similar triangles. Okay, so there's our free body diagram. Now it says calculate the magnitude of the tension in the rope. Well, we want to get the tension. And notice that everything has to balance out to 0. And so this tension is acting in this direction. The only other thing acting in that direction is this component of gravity. And do you see how I've sort of tilted my axes here? So what I'm saying now is that this is sort of my x direction, and this is sort of my y direction. The direction of tension is x, and the direction of the normal force is y, and it's all tilted. That's going to make my problem a lot easier to solve. So let's take a look at this here. If I say that x is in the direction of the tension, well, I know that the net force in the x dimension is 0, because the net force in all directions is 0. So, I can say here the net force in the x dimension is equal to 0, which is equal to, now I'll just look at the net force in that dimension. So I have tension going to the right, and Fg sine 25 degrees to the left. So that means that I can rearrange this equation. I can rearrange that to solve for Ft. So I can say Ft is equal to Fg sine 25 degrees. Now Fg, we know, Fg is equal to mg, so now I can substitute that in. So Ft is equal to mg sine 25 degrees. And that guy is 14 kilograms times 9.8 sine 25. And now I can get my answer here. So I have 58 newtons. And that tells me my tension in the rope. And you see how that worked pretty well when I used my x and y directions the way that I did. Okay. Now we want to calculate the magnitude of the normal force. Well, that's great. That's our y direction. So the net force in the y is equal to 0. So I can say 0 is equal to normal force acting upwards minus Fg cosine 25 acting downwards. This means that Fn is equal to Fg cosine 25 degrees. And same thing, I can write that as mg cosine 25. Fill in the numbers. 14, 9.8 cosine 25. And that gives me 124 newtons, which I need to put down into 2 digits, 120 newtons. The end. So, that was our first example, solving that sort of a problem. We have a second equilibrium problem. It says your car is stuck in the snow. You tie a rope to it, then you and your friend pull the rope with a force of 10 to the 3 newtons, but it doesn't move. So to start with, we're saying, here's some car, here's some rope, we're both pulling at it with 10 to the 3 newtons. That's not enough to pull the car. Okay. Then you try tying the free end of the rope to a tree and pulling on the rope in the middle. So like the picture in the left here, or sorry, in the right. So here's our tree, here's our car. We are pulling in the middle of this rope, and you can see that we're pulling this rope downwards, which means that there's something happening to the right and something happening to the left now in this rope. Whereas before we were just pulling on the end of the rope. Okay. So, let's see. Now that we're doing this, the car just starts to move. The car just starts to move, which means it's not accelerating, but it's just starting to move. So we still have equilibrium, but we're right at equilibrium now. So what tension force does the car experience, and why does this work? Okay, so we'll draw the situation again. We draw a free body diagram. And I'm going to draw the free body diagram of this. Not of the car, but of what's going on right here in the middle. Because that's the thing that's getting all these forces. You can see I have tension going off to the left, tension going off to the right, and applied force coming down. So that's what I'm going to draw. So here's where we're pulling on the rope. We have an applied force of still 1,000 newtons. That's still how much force I can pull down. Which means then we've got tension here, tension here. Okay, and we're told again that this situation is in equilibrium, so we can say the net force again is equal to 0. So we can use this picture to solve some questions. I'm going to draw in the angles that we were given here. So we're told that yes, we're told that the angle here is 10 degrees. 10 degrees here, 10 degrees here. Good. So now I can say, since we're in equilibrium, I can look at my net x force, which is equal to 0. And if we look at that, that makes sense, because to the right we have just the tension force, to the left we have the equal tension force. And remember that since this is a rope, it means that in both directions the tension force has to be the same, because the tension is constant throughout that rope. So, this is just, I mean, it makes sense. We have Ft cosine 10 degrees minus Ft cosine 10 degrees. So that hasn't really given us any information. That makes sense that that's 0. But let's try y. This also has to be equal to 0. And this is equal to, going upwards, we have Ft sine 10 degrees plus another Ft sine 10 degrees. And then going downwards, we have our 1,000 newtons, which was our applied force. Okay, so now we have something we can work with here. I can say that 1,000 newtons equals 2 Ft sine 10 degrees. And now it's simple matter of rearranging to find Ft is equal to 1,000 newtons over 2 sine 10 degrees. And I will put that into my calculator, and it will give me 2879, sorry, that's a 72879 newtons. And I'll round that off again to a nice 2900 newtons. So there we go, that's the tension and the force, which means that if we look at the car, that's how much force the car is experiencing now, which is kind of cool because we can only pull with 1000 newtons, but the car ends up experiencing 2900. We're getting way more out of our pulling just by doing this. So the second question is, why does this work? Well, if you haven't sort of thought about it already, just give it some thought. What we're doing here, we've tied it to this tree, which means now when I pull down, the tree is pulling back. So all this extra force that we're getting is coming from the tree, because the tree is saying, no, I'm not going to move. So it's giving us a whole bunch of extra force when we pull, and that is feeding along to the car. So that's where we're getting all this extra force from. All right, we'll go to the next page. And those were our two equilibrium questions. Now we're going to look at questions that aren't in equilibrium. And so now we're dealing with, I guess, for the first two problems, we'd be dealing sort of with Newton's first law, where we're saying there's no net force, so there's no acceleration, everything's moving at a constant speed. Now we're dealing with Newton's second law, where we do have a net force. We're going to say that the net force is equal to mass times acceleration. Okay, and just like in the very first problem we looked at, we're going to use this trick of changing our positive x-axis to a convenient direction. We're going to use this from now on. So the trick here is that we set the positive x-axis. So we set this to be the direction of the net force. And that's also going to be, and the direction of the acceleration, because we accelerate in the same direction as our force. So we set our positive x-axis in the direction that we're accelerating. That makes solving a lot of these problems a lot easier. So we'll see how that works in this first problem. A sled is at the top of a hill which makes an angle of 18 degrees with the horizontal. The height of the hill is 25 meters. Calculate the speed of the sled as it reaches the bottom of the hill and assume that no friction acts on the sled. Okay, so our acceleration clearly is going to be straight down the hill, so that's going to be our positive x-axis. I will draw my free body diagram, and there's only a few things going on here. We have gravity. We said that there's no friction on this hill because it's snowy and icy, so we just have the normal force as well. Normal force. And so we've said that the direction of acceleration is going to be our positive x-axis. So this is x. This is going to be y. And actually we call this y hat and x hat when we're talking about directions. Don't worry too much about that. Just x and y. And yeah, we'll need to fill out some directions. So we're told that that this hill is 18 degrees to the horizontal. So it looks like this, which means that this remainder here is going to be 72 degrees. And that's going to be useful if I want to break this gravity component into perpendicular components. And sorry, I'm just going to squeeze that in there a bit better. So we've got 72 degrees. And then gravity, you can see I can make this perpendicular components now using the x and y directions that I've just created. So you can see now I have a triangle for gravity with an x and y component. So if I was to draw again my directions, look something like this. This is y and this is x. Okay, excellent. So we know that the net x force, well, if we look at this picture here, we only have two forces. And the normal force is acting in the y direction. And that's going to be cancelled out by this piece of gravity. So really our net force here is going to be, I can solve this first here. I'll just put the y, and I'll say the net y force is going to be equal to 0 because it's not accelerating into the hill at all. It's just accelerating down the hill. So the net y force is equal to 0, and that's also equal to Fg sine 72 degrees minus Fn. So another way of saying that is that the normal force is equal to Fg sine 72. But in this problem, we don't really care about the normal force. What I want to find is my x force. The net x force is going to be just this Fg cos 72 degrees. Just this piece. That's what I'm interested in. And that force is what's going to make me accelerate. So this is equal to mg cosine 72 degrees. And that's great. Now we don't know the mass, right? Notice that we don't know the mass. So we're going to have to sort of go forwards. We have our net x force, and we're going to have to figure out what we can do with that. So I can say that my net x force is going to equal to my mass times acceleration, because that's the only force that this thing is experiencing. Okay, so we have mg cosine 72 degrees is equal to ma. And that's kind of cool. Mass, those cross out. So then I can say that A is equal to g cosine 72 degrees. Cool. And then I can solve that. Right, I have A is equal to 9.8 cosine 72 degrees, which is equal to 3.0 meters per second squared. Excellent. Now I have an acceleration. Now I can do some kinematics problems. So I am going to have to figure out how long it takes to travel this distance here. Now again, I'm going to need to figure out what that hypotenuse piece is. We're told that the height of the hill is 25 meters. So if I just draw my hill again over here, I have my hill. I can say that this is 25. This was 18 degrees. So if I want to find my displacement here, well, displacement is going to equal, how can we do this? I'm going to say that the sine of 18 degrees is equal to 25 over the displacement, which means that this is equal to 25 over sine 18 degrees, and that will give me 80.90 meters. Perfect. And then I take this value back over here, and I can use my equation. So I'm just going to use my kinematics equation that uses, I know that my, I want to find the final velocity, and I know the initial velocity is 0, and I know acceleration and displacement. Perfect. So vi squared plus 2a delta d, and this whole thing is just equal to 0. So now I can say that vf is equal to the square root of 2a delta d. That's the square root of 2 times 3, or 3.0, times 80.90. That gives me a value of 22 meters per second. Okay, and you see, that was a kind of a fun problem because it combined, finally, our kinematics and our forces. We've got all sorts of different things going. We've got 2D motion in here too. There's all sorts of fun things in this problem. Okay, we've got one more problem here, and I might leave some of this for you. Let's just get it set up maybe. So it says a crate with a mass of 32.5 kilograms sits on a frictionless surface and is connected to a second crate by a string that passes over a pulley. The second crate has a mass of 40 kilograms. The pulley is frictionless and has no mass, and the string also has no mass. In physics, we pretend things don't have mass. Determine the acceleration of the system of crates and the magnitude of the tension in the string. So remember here, if I've got some tension in the string here. It's the same tension in the string here. The tension is constant throughout the string. And we're actually going to be using that to solve this problem. So to do this, I'm going to set up two free body diagrams. I've got a free body diagram for the top box. So we've got normal force, tension, and M1G. This is just using the first crate's mass. And the second one here, we've got tension acting upwards, and we've got M2G here, acting downwards. So if I do my net X force, well, you can see that the Y forces cancel out because it's just sitting. This one's just sitting on top of the table. So the net X force is equal to Ft, and net X force, this is going to be its mass times its acceleration. Net force is equal to m1a. So we have here, this is equal to Ft. That's as much as we can say here about that situation. So now I'm going to set this guy up here. We can say that the net Y force, well, I'm just going to sort of do a funny thing, and I'm going to say that X is the direction along the string. Okay, X is this direction. So X sort of bends at that pulley, and that's a funny thing that pulleys do, is they can sort of change our coordinate system. So I'm still going to call this X, but it's just a way of thinking about it. It's not too much of an issue. So you can see this M2G downwards minus our tension force upwards. So our net force here is M2A is equal to M2G minus tension. Good. And I did all sorts of vector arrows here. I probably should have left those off. I'm just going to leave those off for the rest of the problem. But now you can see we have tension on the left. We have tension on the right. We can combine these two statements here. Actually, I'll just rearrange them first. So I'm just going to solve this one to the right here. Tension is equal to M2G minus M2A. So now I can take these two values for tension, combine them, and I can say that M1A is equal to M2G minus M1A. Okay, and now I have a pretty useful formula. Before we go any further, I just want to show you I'm using A, not A1 and A2, because these are both going to accelerate at the same speed. They're tied together by a rope, so however fast this one is accelerating down, it's pulling this one so that it accelerates at the same rate. They have to have the same acceleration, and that helps us to solve this problem. Okay, so we have this nice little statement here, and I can now solve that. So I'll just rearrange. I'll say that M1A plus, oops, and this is here, this is M2A over here. Okay, so M1A plus M2A is equal to M2G. I can factor out the A. Which means that A is equal to M2G over M1 plus M2, which is really useful. So I'm trying to find the acceleration. I've got an equation now, and I can fill in my values. So mass 2 is 40.0, G is 9.8, divided by 32.5 plus 40.0, and this gives me 5.41 meters per second squared. So that gives me my acceleration. And it also asks for the magnitude of the tension. So let's just find that here. We said that tension above, we'll just use either of these equations. So Ft equals m1a. So it equals m1a. And I can fill this in here. That's 32.5 times the value we just found, 5.41, which is equal to 175.7 newtons. And now we should worry about significant digits. So let's see, we have 3 digits. 3 digits. 3 digits looks good to me. So this guy is equal to 176 newtons. Our acceleration was already in 3 digits. That's perfect. We're all done. Okay, that's that full lesson. Let me know if you have any questions, and I'll see you in the next one.